You don't need numbers or fancy equations to prove the Pythagorean theorem. All you need is a piece of paper. There's a ton of ways to prove it, and people are inventing new ones all the time, but I'm going to show you my favorite, except instead of looking at diagrams, we're going to fold it. First, you need a square, which you can probably obtain from a rectangle if you ask nicely. Step 1, fold your square in half one way, then the other way, then across the diagonal. No need to make these creases sharp. We're just taking advantage of the symmetries of the square for the next step, but be precise. Step 2, make a crease along this triangle parallel to the side of the triangle that has the edges of the paper. You can make it anywhere you want. This is where you're choosing how long and pointy or short and fat your right triangle is going to be, because this is a general proof. Now when you unwrap it, you'll have a square centered in your square. Extend those creases and make them sharp, and now we've got 4 lines all the same distance from the edges, which will allow us to make a bunch of right triangles that are all exactly the same. Step 3, fold from this point to this one, basically taking a diagonal of this rectangle. Now we've got our first right triangle, which has the same shape and area as this one. Let's call the sides little leg, big leg, and hypotenuse. Rotate 90 degrees and fold back another triangle, which of course is just like the first. Repeat on the following 2 sides. The original paper, minus those 4 triangles, gives us a lovely square. How much paper is this? Well, the length of a side is the hypotenuse of one of these triangles, so the area is the hypotenuse squared. Step 4, unfold, and this time let's choose a different 4 triangles to fold back. Rip along one little leg and fold back these 2 triangles. Then you can fold back another 2 over here. The area of the unfolded paper minus 4 triangles must be the same, no matter which 4 triangles you remove. So let's see what we've got. We can divide this into 2 squares. This one has sides the length of the little leg of the triangle, and this one has sides as long as the big leg. So the area of both together is little leg squared plus big leg squared, which has to be equal to this area, which is hypotenuse squared. If you called the sides of your triangle something more abstract, like a, b, and c, you'd of course have a squared plus b squared equals c squared. So quick review. Step 0, acquire a paper square. Okay, step 1, fold it in half 3 times. Step 2, fold parallel to the edges anywhere you choose and extend the crease. Step 3, fold back 4 right triangles around the square and admire the area hypotenuse squared that is left over. Step 4, unfold and rip along a short side to fold back another 4 right triangles and admire the area one leg squared plus the other leg squared that is left. And that's all there is to it. Of course, mathematicians are rebels and never believe anything anyone tells them unless they can prove it for themselves. So be sure to not believe me when I tell you things like, this is a square. Think of a few ways you could convince yourself that no matter what the triangles on the outside look like, this will always be a square and not some sort of a rhombus or parallelogram or dolphin or something. Or, maybe it is a dolphin, in which case you should define what a dolphin is and then show that this fits that definition. Also, these edges look like they line up together. Do they always do that? Is it exact?